Welcome everyone to today's Explainer. I am absolutely thrilled to have you here. Look, today we are fundamentally changing how you approach the Cambridge Physics 0625 syllabus. I want you to think about answering a physics exam question as being exactly like taking a photograph, right? If you don't have the right camera settings, if your focus is completely off or your zoom is just wrong, your answer is going to be a blurry, unrecognizable mess to the examiner. You might actually have the perfect concept in your head, but without the correct mathematical framing, the final picture is ruined, and those crucial marks literally slip right through your fingers. So today, we're going to master the 4 core mathematical settings you need to represent values perfectly in physics. We are going to calibrate your lens.
To really understand why this is so critical, just imagine walking into a grocery store, walking up to the counter, and asking the shopkeeper, "Can I have 10 salts?" Seriously, what would happen? They'd just stare at you blankly. Do you mean 10 grams of salt? 10 packets? 10 kilograms? You see, a measured value in physics means absolutely nothing without a unit. Numbers without units are exactly like an uncentered, out-of-focus photograph. They are meaningless in the real world. If you write down in your exam that the speed of a bullet train is 500, the examiner has no idea if you mean 500 meters per second or 500 kilometers per hour. We have to give our numbers a physical reality.
So, here is our ultimate camera manual for today's session. We're going to master 4 fundamental skills to stop you from losing those easy exam marks. First up, framing the variables, understanding exactly what we are measuring and the units we use to measure it. Second, the symbol shorthand, learning the universal language of physics to save you precious time on the clock. Third, focusing significant figures, making sure your answer is neither heavily pixelated nor artificially over-sharpened. And finally, zooming with standard form, how to easily handle the impossibly massive and the incredibly microscopic numbers that literally define our universe.
Okay, let's dive right into this. Our first setting is framing the variables, because before you can solve any problem, you have to define exactly what is in your frame. If you don't know what you're looking at, you can't possibly measure it correctly. But hey, before we continue, subscribe to our YouTube channel, Ace the Exams, at acetheexams_IGCSE to excel in your Cambridge examinations. Click that subscribe button and hit the bell icon right now. All right, let's get back to framing those variables.
So there is a very clear distinction we need to make between a variable and a unit. A variable is simply a measurable characteristic. Think length, time, mass, temperature. These are the variables that help us describe features of the real world. But the variable itself just isn't enough. Every single variable has to have a unit linked to it. The unit is the standard that actually allows us to understand the scale of that variable. For example, the time sunlight takes to reach the Earth is a variable, and its value is 8 minutes and 20 seconds. The mass of the moon? That's 7.3 times 10 to the power of 22 kilograms. The mass of 1 liter of water is 1 kilogram. The unit gives the number its anchor in reality.
And to make sure everyone across the globe understands your measurements, scientists have agreed on a standard set of units called the SI units, or Système International. The variable of length, or distance, is measured in meters, with the symbol lowercase m. Mass is measured in kilograms, with the symbol kg. Time is measured in seconds, with the symbol s. If you use these consistently, your calculations will always translate perfectly. Now let's keep building on this. A completely crucial mathematical skill here is choosing the correct unit during calculations. If you're calculating area, which as we know is length multiplied by width, both measurements must have the exact same unit. If your length is 20 centimeters and your width is 10 millimeters, well, you must convert that 10 millimeters into 1 centimeter first. Only then does 20 centimeters multiplied by 1 centimeter equal 20 square centimeters. Consistency in your frame is everything. Awesome. Let's move to our second setting, the symbol shorthand. Listen, in an exam, time is your absolute most precious resource. We need a way to write down our framed variables fast. Just look at the left side of this comparison. Weight in newtons equals mass in kilograms multiplied by gravitational field strength in newtons per kilogram. Writing word equations out like this is incredibly clunky and slow. Now look at the sleek, universal shorthand on the right. W equals m times g. Or simply, W equals mg. In symbol equations, we often just drop the multiplication sign entirely. W stands for weight in n. The symbol inherently includes both the numerical value and the unit. It's faster, it's cleaner, and it's instantly recognizable to any physics examiner marking your paper. Because this shorthand is so essential, you absolutely must memorize the symbols for each variable. Most variables in physics are represented by single letters. And honestly, I highly recommend making flashcards to master them. On one side, put the variable energy and its symbol capital E. On the other side, put its unit joule and the symbol capital J. But a huge warning here, and I see students lose marks on this all the time. Case matters immensely. Because there are only 26 letters in the alphabet, letters get reused. A lowercase m can represent the unit meter, but it can also represent the prefix milli. And if it's an italicized lowercase m, it represents the variable mass. A capital V represents both the variable volume and the unit volt. Never, ever make up your own symbols in an exam, and take absolute care to use lower and uppercase letters exactly as they are defined in the syllabus.
All right, we are rolling. We've arrived at our third camera setting, focusing significant figures. This is all about the precision of your measurement. Remember our photo metaphor? Too few digits and your picture is heavily pixelated. Too many and it's artificially over-sharpened.
Significant figures dictate exactly how precisely you actually know a number. For example, a measurement given as 2.34 meters has 3 significant figures. It tells us we know the measurement to the nearest 0.01 meters or 1 centimeter. Now, how do we count them? This is the golden rule. Reading a number from left to right, the very first significant figure is the first digit that is not a zero. So, in the number 0.06500, the first significant figure is the 6. The zeros before it, they're just placeholders. In the number 700,560, the first significant figure is the 7. Often, after doing a calculation, your calculator will spit out a massively long number. You'll need to change it to a specified number of significant figures, which involves a process called rounding. Rounding is really just expressing a number as an approximation with fewer significant figures. The steps are beautifully simple. To decide the value of your final significant figure, you just look at the very next digit. If that next digit is 5 or greater, you increase your final significant figure by 1, you round up. If that next digit is less than 5, you keep the final significant figure exactly the same. Let's look at a concrete example to lock this in.
Let's say we have the number 546,520, and the exam asks for it in 2 significant figures. Our first significant figure is 5. Our second significant figure is 4. That is exactly where we want to stop. So we look at the third figure, which is the next digit over. That digit is a 6. Because 6 is greater than 5, it triggers our rounding rule. We must round the previous digit, the 4, up by 1. Therefore, the 4 becomes a 5, and the rest of the numbers just become 0 placeholders. Elegantly, 546,520 rounded to 2 significant figures becomes 550,000. Here's another quick one straight from the source. What if a density experiment yields a volume of 0.5236 cubic centimeters, and we need it to 2 significant figures? Well, the leading 0 doesn't count. The first sig fig is 5. The second is 2. The third digit is a 3. Since 3 is below 5, we completely ignore it and everything after it. The answer simply becomes 0.52 cubic centimeters. Focusing your answer perfectly like this secures those precision marks every single time. Stop scrolling. Subscribe to our YouTube channel Ace the Exams, at @acetheexams_IGCS to excel in your Cambridge examinations. We've helped thousands of students improve by 2 to 3 grade boundaries. Join them right now by subscribing to @acetheexams_IGCE and turn on all notifications so you never miss our weekly exam strategy sessions.
Okay, let's move to our fourth and final camera setting, zooming with standard form. In physics, we deal with the absolute extremes of the universe. We study the incomprehensibly massive and the incredibly microscopic. Working with these extreme numbers using ordinary decimals is an absolute nightmare, and it's a guaranteed way to make simple addition or counting errors under exam pressure. Standard form is our zoom lens.
Just look at this comparison. On the left, we have the mass of the Earth written out in full, 5,972, followed by 21 zeros in kilograms. Imagine having to write that out 3 times in a single exam calculation. The chance of missing a zero and ruining your whole calculation is huge. Now look at the visual relief on the right side. 5.972 times 10 to the power of 24 kilograms. This isn't just shorter, it's practically immune to zero counting errors, and it makes it incredibly easy to compare with, say, the mass of the Sun, which is 1.989 times 10 to the power of 30 kilograms. Standard form is a total lifesaver.
So what exactly is the rule here? Standard form is a specific notation where a number is written as a value between 1 and 10 multiplied by a power of 10. A number larger than 10 is written with a positive power of 10. It's like zooming out. For example, 100 is 10 times 10, which is 10 squared. So 500 becomes 5 times 10 to the power of 2.
Conversely, a number smaller than 1 is written with a negative power of 10. This is zooming in. 0.001 is 1 divided by 10 3 times, which is 10 to the power of negative 3. So, 0.006 becomes 6 times 10 to the power of negative 3.
To make this even faster, physics uses unit prefixes as the ultimate zoom shortcuts. A prefix is simply a term added to the front of a unit name to indicate a power of 10. For instance, giga means 10 to the power of 9. Mega is 10 to the power of 6. Kilo, which we use all the time for kilograms and kilometers, means 10 to the power of 3, or 1,000. Going smaller, milli is 10 to the power of negative 3, micro is 10 to the power of negative 6, and nano is 10 to the power of negative 9. Trust me, the thickness of a piece of wire is much easier to understand in millimeters than expressing it as some tiny, confusing decimal of a meter.
Let's actively put this into practice with a challenge straight from our textbook examples. Imagine an exam question asks you to convert 0.01 millimeters into base unit meters, and you must give your answer in standard form. How do we approach this? Well, we combined everything we've learned today.
Let's break it down step by step. Step 1, we look at the prefix milli. We know from our unit prefixes that milli stands for a multiplying factor of 10 to the power of negative 3. Step 2, we remove the m for milli and replace it with its numerical equivalent. So 0.01 millimeters becomes 0.01 times 10 to the power of negative 3 meters. But wait, step 3 is vital. The number 0.01 is not in standard form because it is not a number between 1 and 10. We have to adjust it. 0.01 is actually 1 times 10 to the power of negative 2. When we multiply that by our existing 10 to the power of negative 3, the rules of power say we just add the indices. Negative 2 plus negative 3 is negative 5. So our final perfectly framed answer is 1.0 times 10 to the power of negative 5 meters.
And that brings us to the golden rule, arguably the most important takeaway for structuring standard form answers correctly. In standard form, the decimal point always goes after the first significant figure. Think about the diameter of a microscopic smoke particle undergoing Brownian motion, which the text tells us is 0.000000035 meters. The very first non-zero digit, the first significant figure, is the 3, so the decimal point absolutely must go immediately after it, giving us 3.5. Because we had to move the decimal point 8 places to the right to get there, it is 3.5 times 10 to the power of negative 8 meters. Burn that quote into your memory. And hey, here's your final reminder. Subscribe to our YouTube channel, Ace the Exams, at acetheexams_IGCSE to excel in your Cambridge examinations. Subscribe right now to @acetheexams_IGCSE and click that bell. Don't let another exam pass you by.
So, we have built a complete manual today. Framing the variables with correct units, speeding up with symbol shorthand, focusing precisely with significant figures, and zooming flawlessly with standard form. If you apply these 4 settings to every single numerical question you face, you will stop dropping those frustrating, easily avoidable marks. I want to leave you with this provocative thought. What is your target Cambridge physics grade? And if you are completely honest with yourself, which of these 4 mathematical camera settings is currently costing you the most marks? Drop a comment below with your target grade for physics and the biggest challenge you're facing. Our team responds to every comment. Like and share this explainer with a study partner. Ace the Exams, your Cambridge success starts here. Thank you so much for joining me today, and I'll see you in the next one.